So we continue our lecture. So why we need PCA? Why we need an eigenvector? Okay. So this is one example. This is page 33. Page 33 is one example. Suppose we have 3 points in the xy space. xy space. So our purpose is try to use LDA, suppose, or some discriminator, 就是分类工具, try to classify and discriminate the 3 samples. Each sample, suppose, is one face. So one face, 2D face, one face. So if we project to x-axis, x or y, what's the distance? The distance is closer, is meaning you are not easy to separate. So this distance is closer. And so both were not easy to discriminate. And this one is easy. If we project to the y-axis, y-zone, you'll find both are project this distance between both distance. You project here, this project to here, this project to here, project, and this closer. So can you find a space in the space that the three samples can separate far away? 你要找一个空间，让这些物体分得越开越好。是 PCA. So after we do the PCA, you'll find this one, this eigenvector. This eigenvector can that the 3 points separated as away as possible. So there's a concept for the PCA. So the same as this one, this 2D. Suppose this page is 35. Suppose your samples here. Can you find a space, and that space where that each sample can be separated as away as possible? So you'll find this is one cluster. So you'll find a center point. So original is here. You move to here. So the translation. And this one is based on the sample. All the samples, you find an average value in the middle. So this one actually is what we talk about. We just talk about this one. Based on all the samples, you try to find the average value. Average of the distribution. So you find the average value. So from here, you shift to here, this end. And this one is an eigenvector. One eigenvector, because you have 2 dimensions. 1 dimension, 2 dimension. So here we go. Eigenvector 1, eigenvector 2. And for this one, this eigenvalue, you'll find, that's what I say. The maximum eigenvalue 1 will corresponding to eigenvector 1， 就最大的 eigenvalue 这个空间，这个 eigenvalue 这是 eigenvalue 在这里 ，eigenvalue 最大的 eigenvalue 表示它的分布在沿着这个轴，这是 eigenvector 1， 这是 eigenvector 2。这个就是 eigenvalue 2， 这边到这里，这变成一个椭圆，这变成一个椭圆。那椭圆就是高纬度的高旋。So original space after you find eigenvalue 1, corresponding eigenvector 1, eigenvalue 2 here, corresponding eigenvector 2. So this will become your eigenspace. And eigenspace, the distribution of eigenspace is meaning the eigenvector 1 have the largest variance, this eigenvalue. Eigenvector 1 responding to largest eigenvalue. Eigenvalue is a variance of Gaussian model. That's meaning along the eigenvector 1, each point project on the eigenvalue 1, they can separate largest, 最大. And then project to this eigenvalue 2, they can separate the second one. For example, if I want to recognize the face, my eigenvalue 1 is the eyes, my eigenvalue 2 is mouth. And so based on the eigenvalue 1, you project on eigenvalue 1. We have most of people, we can recognize probably 60% of people based on eigenvalue 1. 60%分出来. In eigenvalue and eigenvector 2, you can separate probably 20%. And the eigenvalue 3 will be 10%. So you just do this kind of separation. Finally, you can separate to individual one. That's eigen PCA. OK， 这样听了。那我们开始讲数学史啊。We talk about mathematics. And talk about mathematics, I will go back to here, page 30. So suppose we have this image. For my lecture, in the last page, we'll talk about reference. And this lecture based on this paper, even though it's old, but it's important. To here. Page 30. So suppose we have 16 persons, still good, 16 persons. So this is the image for each person. The image size is suppose it's sort of 128 by 128. First of all, we try to find the average face, 平均的人脸. So it's page 32. This average face, because we need to find the mean value. 我们找到这个平均的人. So each time, each one we subtract with the average value. Sorry, this average value we set here, we call unbiased. So each image we subtract subtracted by the average value become the new image. This new image look like this one. 原来影像经过平均变成 extract 这个影像出来。So we have a basis. 我们有个每个都有标准这样子。So this is pre-processing. So this is the result. So after we do the pre-processing, this A here, this A, 这是我们处理过的哦。这个 A 就是 page 这里 ，page 30是这个 A， 这是我们有30张16张影像嘛。那每张影像都做相近以后，我们到这里的时候，这有16张unbiased影像。那 next step is the A, we try to do the covariance matrix. And based on covariance matrix, we try to separate to become this one. Eigen, sorry. Become eigen. This page is 39. Based on the covariance matrix, we use singular value decomposition UW. Because this is symmetry, so V equal to U， 这是对称矩阵。原来的不认识嘛，经过因式分解变成 U。And this is eigenvalue is eigenvector. In page 37 here, just that you know how can we check the covariance matrix. You can do this way. Use II. II is easy. Use II and use this one. So covariance is equal to this one. 这个好，那这没什么，这是跟你讲一样，讲这件事情。So page 39 is for each covariance matrix. After you do the singular value decomposition, become eigenvector. So eigenvector will be this one. This is U. So this is eigenvector 1. Sorry, the eigenvector. But they don't sort it. So you do sort by yourself based on the eigenvalue. So what's the eigen? Eigen is orthonormal. Because eigen is the axis. Eigen 是一个轴，每个轴是一个 eigen。eigen 是一个轴，这 eigen 是一个轴，是一个轴。那每个轴的条件是它一定要 orthogonal， 就 orthogonal 轴与轴跟90度 orthogonal and non-violation 就是 univector。就这个要单位的那个向量 univector 面积等于1，所以这个 normal 乘以1，每个都 normal 来乘以。The eigenvector is the orthonormal axis. So orthogonal 它是垂直。那 why we need orthogonal? It's meaning eigenvector 1 is independent to eigenvector 2， 独立才办法相加。Why we can do the linear combination? Ax plus by, xy, they are orthonormal. Orthonormal meaning the x is independent to y， 两个不互相影响，才可以拆解出来。拆解你才办法算，不拆解你没办法算，所以要 orthonormal。So eigenvector 1 orthonormal to eigenvector 2这样子。好，那这个你自己看，这个就不讲了。那这是一个一般的数学式啊，一般 how can we solve eigenvector eigenvalue? This is regular simple. This is only 2 dimension. But our eigenspace is high dimension. You cannot use this way. So suppose 2 dimension 这2维的话，那数就这样子，这 covariance 是我们在讲的这个数学式，就是就这个数学式一模一样。我把 U 移过来 ，CU equal to UW 就这个一模一样，不要搞混了，这个一模一样啊。I try to solve eigenvalue and eigenvector. So how can we solve? We know this one. We already know C. So how can we solve U lambda? So use this one. So after we solve this one, so suppose we have example. This one example. Suppose we have 4 points. And 4 points like this one. 1, 2, 3, 4. Yeah. So in xy dimension, based on the distribution, based on the function distribution of 4 points, how can we find eigenvector and eigenvalue? The traditional method will use this one. But it's only for two dimension or 3 dimension. But in our image is high dimension, you cannot use this one. You directly use the SVD. But to here, so if we took only 2 dimension, this one example. So if you find the mean value is meaning, see, mean value is 3, 4, right? This distribution, you find mean value. The mean value is 3 and 4. That's meaning this point. 这一点是3跟4。就是这些 distribution 中心点就是 this point 3 and 4， 所以 from 0, 0 you shoot to the mean here. and then you try to find this new coordinate, this original coordinate, this new coordinate based on the new center 3 4， 在新的空间的向量这样子，有正有负。那你根据就找出这个，你要找出这个希望，这个找出来，然后再找出 eigenvalue， 最后你会发现 this is eigenvalue 1， this is vector 向量，一个轴两个轴就这样，这个就是你的新空间。This is your so this space meaning for the eigenvector 1, you can separate all 4 points as away as possible。这样算出来，就是一般的例子啊。继续，这个因为我已经快讲完了。So after you find the eigenvector, right? So then for original space, you want to project projection weight. So we talk about projection weight here. That's meaning for each image here, you subtract with the average value as mean shift to the eigenspace. You project to each axis. Each axis is meaning each eigenvector axis, and you have projection weight. So suppose you have 16 images, so your projection weight is 16. 你有16张影像，你 project 到这个空间就变成16个值。因为你有16张影像会产生16张 eigenvectors， 那每个 eigenvector 就是一张影像，那你把它 project 下去就16个值。那重点不在这里。The important thing is not only we can try to find eigenspace, the other important thing we want to reduce the dimension. So original we have a page 58. So suppose original we have 16 images. We try to find average image, and then actually we have a 16 eigenfaces. You have only you have 16 images, you create 16 eigen images. However, your eigenvalue in this case, after eigenvalue number 8, the eigenvalue will be close to the 0. That is meaning those eigenfaces are not important. You can ignore that one. 你16张影像产生16张 eigenspace as eigenface， 但是我们根据它的 eigenvalue 收听完以后，你会发现，像这个例子来讲，第8个 eigenvalue 值就接近0了。0代表什么？代表这里面有 valence， 就这些 eigenface 不重要了。So that's meaning you can just pick up the first 7 eigenfaces and you ignore others. 那些不重要的，那这些你就可以让你做 discrimination。所以回到这一边 ，so that's meaning the origin any image you project to the eigenspace. So original you can project to 16 images, 16 images eigenfaces, but you only need the first 7. So your eigenspace from 16 becomes 7. That's meaning any image you project to the new eigenspace, you only have just keep 7 projection weights. This 7 projection weights can represent your original image. 就是说你把任何一张影像投影到这个 eigenspace， 可是 eigenspace 不是16张，因为我们后面不重要了，我们只保留前面7张。那意思是说，每一张会对应到一个 projection weight W。那所以每一张256×26影像 project 到那边的时候，你只要变成它只要7个值，就可以代表这一张。就是我们一开始讲的这个。 那就省掉空间。你本来是256乘256维呢，现在变成7维而已。就这里，我会讲这里。For any image, you can become like a projection weight and only keep first seven projection weight, and other if you don't know it. So you have 7 projection weight to represent your original image. 被7维，就你本来原来影像假设有256维，那你要做 NCC 做 SAD， 你要那个256乘256维这样去比，这样只要7个维度来比较好。像我们以前公司美国最好的人脸辨识公司，1分钟可以辨识100万个人脸，一些搜寻，一些辨识这样子。为什么？因为我们每一张人脸的 projection 会只有一点点，这是 PCA 的作用。那这个就是你最后这7个维度的 eigen， 7个维度的这个 eigen 的东西，就是你的 encode 的那个 code 码。projection 下去就是 projection weight， 是你的边的那个系数这样子。所以就这个，你编码是这个。再回到原来这里，被做回去，这样可以吗？好，那现在有个问题啊。So how many? So this is m prime is meaning only 7 in this case. M is 16 in this case, in 16 phases. But right now m prime is 7. So how can we decide the number of eigenvector we want to keep? So this is one example here. So that means suppose we have an image, total image 932. 那么我们932张影像。Okay, so how many faces we want to keep? Only 10. Why? Because this is the equation. This is a summation or eigenvalue. Eigenvalue, okay, is meaning for each one. So we have 932 images. After we do PCA, we have 932 eigenfaces. Each eigenface will corresponding to one eigenvalue here. Okay, so you sum of the eigenvalue together become the denominator term. So this one accumulated. So first you do the sorting. So the first image, first eigenvalue probably will take 60% overall eigenvalue, and accumulate, and until you accumulate this one until suppose 96 or 98. Here you cut, and others are not important. You ignore this one. So in this case, because I accumulate, after I sort the eigenvalue, at plus 1, plus 2, plus 3, until I plus 10, it already more than 96%. That's meaning most of energy, most important feature is put in here. So after 96, I ignore. So that's meaning my dimension will reduce from 932 to 10. So PCA, basically PCA can reduce a lot of space. That's the PCA 这样决定的。对，那最后这里这剩下你自己看啊。PC 有什么好处 ？PC 有什么好处 ？Is this one. So you input one image and project and then recover. See a little bit blur. Why? Why is blur? Because you reduce some detailed information. Originally you have 16 images, but now it become only 7 eigenfaces. So some information you lose. 那这个是它的例子啊，这个例子做不好是什么原因？不止那个，它实际上是没有做 alignment， 就是 the other problem they don't do alignment eyes， 就那时候做没有忘记 align， 然后以前公司有 align， 所以我们做出来会很漂亮。这个模糊的两个原因，一个是 why is it two reason why is they don't do alignment based on the eyes。One important thing is that support if you input this one, you can recover. Now that's 这一页吗 ？Sorry, I stop again。他要继续录吗？我停下来。可以哈，谢谢。Okay, so the PCA can do is let's talk about this page again. Can do analysis, 分析, but also can do the synthesis, reconstruction. That's meaning if you have you lost information here, you project this image to the eigenfaces, eigenspace. You have projection weight. Based on projection weight, linear combination with eigenfaces, you can reconstruct back to here. Because your eigenspace has all the facial information. So that's meaning I wear the mask. And if the eigenspace has enough of my faces, I project to the eigenspace, and then it can reconstruct my face without mask, and then I can do face recognition. So when you try to recognize the face based on the mask, actually, I don't know how others do, but I did not did. But if I do, I will try to take a lot of your photo, become one eigenspace, and then you have a wear mask. I will project like this one, project your face to the eigenspace, and I can reconstruct your face without mask, and I do recognition based on this image. So I recognize your face, not this image, this image. 是这样啊，所以在做 mask 的脸辨识不是辨识你直接变色，是要把它对抗转回来这样子。好，那我们来看一下那个一样在这里。If you project the flower to the face eigenfaces, it will also reconstruct the face because your eigenspace is faces. 因为你的 linear combination 都是人脸上面的，所以 you project to the eigenspace, you can projection weight based on linear combination of projection weight and the eigenfaces, you can reconstruct the face 是这样子。 这篇 paper 有个贡献，这虽然很久，他跟我同时代的，他是那个 Major Turk 的很好，个子很矮，跟我一样，在美国算矮的，跟我一样高，MIT 的，有时候会跟 MIT 的学生碰在一起。So this one is before GAN. This paper contribution of this paper. They use neural network to do the PCA. Original PCA is only mathematics, but this paper, one contribution, it uses neural network to represent the PCA. And right now we use GAN to represent the PCA. It's better. Okay. So I talk about this one. So this original image right here, and this average image. So they do subtraction here. So it's unbiased. Bias means 偏移嘛 unbiased 不偏. So before here, this is pre-processing. When you do the deep learning, right now, here you also divide it by standard deviation and normalize between -1 and 1. Here, this because it's a long time ago, they only, for each original phase, they only subtract with the average phase, become unbiased. Right now, when you do the deep learning, sometimes you are not only do this one, you also divide it by the standard deviation of this one. That's normalization, also pre-processing. 记得你在做深度学习，有很多个深度学习，你如果没注意到，你就把你的影像直接放到 deep learning 里面 network 里面去，你出来的结果不好。有时候是因为你输入的这张影像没有做前处理。什么叫前处理？就是减掉这张影像的平均值 ，pixel 的平均值，再除以这张影像的标准差，做这个动作，结果就不好了。所以有时候做这个前处理，那你基本上做完这个前处理，你的值就介于-1到1中间，差会多一点点，就-1到1，就 normalize， 这是前处理。Okay, so after this one, they try to train, and training. This is the weight of a neural network, and the weight become the eigenvectors. So after you have this 这是一层一层的 like a projection, sorry, like a layer， 你做 convolution 的 layer， 那它这里就产生那个 eigenvectors 在这里，就 network 每个 network 它这里好多层 network， 那每一层 network 就你们现在的 layer 嘛，那每一层 network 那个系数就是 eigenvector 系数。So this one project to here， 这是上你在你们的 deep learning 就是 eigenmap， 对不起，就 heat map 了，或是那个什么那个 convolution 那个 map 这样子。So after project linear and project to the eigenspace, this is the projection weight. So this projection weight become only 7 dimension because here only 7. It's 7 dimension. So that's called projection weight. And you can do recognition based on projection weight. You do face recognition based on the projection weight. 每个人都投影到这里，就变成七个维度的 projection weight， 就可以做 recognition， 做 discrimination 这样子。We can also try to do reconstruction based on the same projection, the same eigenvectors. We do reconstruction. So this is the reconstruction result. So PCA, their input here, the analysis eigenvectors are the same as the synthesis eigenphases. That's no good. It's no good. So your reconstruction result is not so good. OK， 这是它的缺点啊，就是它的这个输入的分析的 analysis 的 eigenvectors 等于它的合成的 eigenvectors， 它直接拿来用了。它创造这个以后直接拿来用，就 reconstruct 回来，这样子。So after you do reconstruction, so suppose if you input phase, you reconstruct a phase, so you do the subtraction, you 比较 you'll find these are similar. So that's a phase. If you do a flower, you project to here, and you reconstruct a phase. So you compare both. This is a flower, this is a phase. So this one is so different. So that's meaning this is not a phase. So here can do phase detection. Here do phase recognition. Here do phase detection. Detection is yes or no. 所以这边可以做 reconstruct， 可以做 face detection， 这可以做 face recognition， 就这样。那后面大概我都讲完了。那这边就讲那个 icon 的东西。那这个不好，所以我们 right now we change to be the PCA. So on my lectures, page 72, this is the original PCA. You put original image into this is projection code, 编码嘛，and projection weight. Based on projection weight, this projection weight, 30 dimension projection weight, we reconstruct because this is the same as this one, the same as this one. So your reconstruction result is not good. But GAN is this analysis different from synthesis because this training is also training. You can get this result from the training. So these coefficients WB are different from WB here. So your reconstruction result is better. So we talk about GAN next lecture. So we continue to talk about. So we finish the PCA and we talk about the LDA. Still have the time. This is PCA. LDA. This is LDA. So what's the purpose for LDA? Linear discriminant function. In the GAN include analysis, include synthesis, also include the discriminator. Yeah, discriminator. GAN, I say again, GAN include the analysis, include synthesis, this generator, include discriminator. It's because GAN is the original one, you do project encoder, decoder, and then do the discriminator. In our lecture, PCA do analysis, do generator, that's PCA. For discriminator, you can use VKLDF. Difference. So in the GAN, they combine because they are network can connect together. Network can connect together. In the computer vision, traditional computer vision, they do PCA and they do LDA. Different. PCA is for space transform. LDA is for discriminator. So difference. So combine PCA and LDA. We equal, not equal. We combine both one. The function is similar to the GAN. For the supportive vector machine, SVM is based on kernel function, project to high dimension kernel function plus the SVM supported vector machine become GAN， 不一样啊，一个是 project， 一个是往上，一个往下，就是 SVM， 一个是 PCA， 但这两个加上 discriminator 就是我们的 GAN 的东西，这样子，让你知道一下。好，那 before we talk about LDA, one very important is we call linear combination. This linear combination, W is a projection weight coefficients. So we do linear combinations. Suppose any function equal to suppose ax plus by plus c, right? A line, 任何一条线嘛 a line. I teach you about discrimination, but at all my lecture, I keep talking about linear combination. And linear combination is an equation. However, when we do the programming, when we do the coding, you cannot write the equation. You should write vector and matrix. So it's AX equal to B province. So AX equal to B province is the same as a linear combination. 你不要两个搞，就两个是一样东西，你不要搞，就是搞不懂。线性的组合 linear combination 实际上就是 AX equal to B， 两个是一模一样的，这样子。我一直强调这一点。好，那我们来看这个数学式。那这个数学式代表一条线，这里有一条，任何一条线。像我们后面这个讲义有这么多条线，每一条直线都是一个 AX plus BY plus C。Sorry, AX plus BY plus C equal to 0是每条线 ，XY is the axis. This is suppose this is high dimension, so they have x1, x2, x3, x4. 它用 x 来代表 y 啦，x1, x， 这是 linear combination. Don't write this way. You should write this way. 刚刚这个数学式这里 ，this one， 这个数学式等于这个数学式。这个数学式你要把它写成像样的形式。内积的形式，这个。So in our mathematics, it's only inner product or cross product， 内积或外积。在做数学运算就是不是内积是外积。那我来讲一遍，这个 linear combination 就是这个 linear combination。那这是 x1 x2 就是 y 的哈 ，x1 xs x2， 那这是它的 projection weight。那所以这个线性方程式，你要把它写成内积的形式，因为老师一直讲，你写程式 you write a code, you cannot write this way. You should write this way. So this is equal to AX equal to 0. AX equal to B, but here B equal to 0. So this means AX equal to 0. But here, this constant term, right? Constant term, 常数项. So this will be AX equal to constant term. So this will be W0 here. Or you can move W0 to here, become W1, W2, W0, and X2 and X2, 1, and 1. Right? X1, X2, 1 becomes 0. So my issue is that any line or any plane, 线或平面 you cannot represent. You can represent, but when you do the coding, you should represent by this format. 你用内积的形式来呈现你的线或平面。那我要讲什么？这 x1, x2 is x's. So what's the w1, w2? 讲是 w1, w2 是 w 什么 because it's the inner product. So W1 W2 is a normal direction of this line. 我再重新再教你数学，然后教你观念问题。这条线 L 假如通过0号，这条线 L 的话就是这条线，这条线的呈现方式用这种方式呈现。那 S1 S2 no problem 是 axis， 那 W1 W2 是什么？就 normal direction， 就这条 normal。那 what's the function for the normal direction？ 法向量的在做什么 ？Control rotation. This one control rotation of this line. That's meaning this line, right? You have a line here, this line, and this normal direction. So normal direction control the rotation. It's important. Normal direction is control the rotation of this line. And this constant term, this one, is a shift from the, suppose this W0 is 0 here. So let's shift. So control the translation. So any equation here, the W, the coefficients control the rotation. The constant term control the translation. So it's an affine transform. 任何这种线或平面的法向量控制旋转角度啊，然后常数项控制位移，又是一种 affine transform。那our purpose is right here. We have one class here, cluster between cross mark and circle. How can we find a line in order to separate both clusters? That's discrimination. Our purpose is try to find a line, right? A line. This line can separate 2 classes or 3 classes. That's discrimination. So based on this kind of a concept, our purpose is try to find a line. 目的是要找出这条线 in order to separate your classes. That's LDA. 那线性的那样子。So next week I will continue talk about LDA. We take a 10 minutes break.